Hi, I'm Ben-Yaakov. This presentation is entitled Illustrative Explanation of Charging and Discharging of Linear and Nonlinear Capacitors. I'd like to thank Evgeny for his assistance in preparing this presentation. Let me say a few words about the background. Capacitor charging and discharging is an important process that is used in many electronic circuits and in power electronics. Despite the seemingly simple action of charging and discharging, the process is really intricate, and there is some misunderstanding, I think, as to what is really happening in various situations. So in this presentation, I'm going to try to explain in an intuitive and illustrative way, it's a different way of looking at things, the charging and discharging of capacitors in various situations. So let me start off very simple with the definition of a capacitor. Now, a capacitor is a device that stores energy. Energy is stored in form of charge and voltage, and the energy is the product of these two. Now, a linear capacitor has a linear relationship between Q and V. This is this linear relationship, and this ratio is defined as the capacitance. Now, this picture is very important in understanding the behavior of capacitors, linear and in particular nonlinear. Now, in a linear case, this relationship, the Q over V, this angle here, is the capacitance, a linear capacitor, but in the case of a nonlinear capacitor, this is not going to be a straight line. This is what is a nonlinear capacitor, and then the behavior is really different. But if you look at this picture, at this presentation, you can use the same tools to handle both the linear and nonlinear capacitor, because this tool gives you the basic fundamental generic relationship between the charge stored and the voltage. So let's start with a very simple case in which we are charging a capacitor from a voltage source. I'm showing here two switches. I'm turning on this switch, and this process now charges C eventually to V in, and I'm assuming that this process is ending, okay, at this point. And then what we see is that the voltage, of course, is rising and approaching V in. The current starts high because the full voltage is on the resistor. I'm assuming, of course, that the capacitor has a zero voltage at the beginning. I'm going to discuss other situations later on. So the current goes to maximum, and then it drops off, of course, exponentially. If we look at this plot here, this space, let's call it, we see that we are starting here. This is the excitation, and now we are moving to this point while the charge is being accumulated. So this is an illustrative presentation of really what is going on. Now, what about energy and losses in this case? So let's take here a slice here and call this height dq and the height v, and then this is energy, incremental energy. So when I take the full integral of it, this will be the total energy, and when using this relationship that Q is C times V, I am getting this CV squared over 2, or I can express it as QV over 2 or Q squared over 2C. This is fundamental. So what we understand now, that the integral of this area, that is this area, represents the energy stored in the capacitor. Now, the energy fed, by the way, let me just say it now, is V in times the charge. Okay, so it's the full square here. Okay, so let's look at it now from another point of view, more specific, and we'll calculate the loss. Again, I'm sort of taking a slice here of dV, height Q, and then this is energy, and I'm taking the integral, and I'm getting the same numbers, of course. So what we see here is that in this case, the total energy going into the capacitor, or into the system, I should say, is this square here, and it's divided by the two areas here. One is the energy to the capacitor, and one is the energy lost. And obviously this process has a efficiency of 50% only, because the same amount of energy is lost, and this is shown here. Now the power is this energy times the switching frequency. I'll usually talk about the energy, and then if you need the power loss, then you have to multiply it by the switching frequency. If this is a repetitive process, I'm talking about like one shot. But if it is a repetitive process, then you have, of course, to multiply it by the frequency. So how can we do the calculation in general cases? There are two ways to do it. First of all, I can calculate this area in the various situations. And then I can calculate the full area and subtract from it the energy of the capacitor to get the losses. Or I can express the losses in terms of Q and V, and for a linear capacitor, using this relationship, I can translate everything to be expressed as a function of the capacitance. So all these are alternative ways, and really there is no advantage of one way or the other, but we are more familiar with actually using the capacitance. But of course, if it is a nonlinear capacitor, then it becomes difficult to use this capacitance parameter. I'll talk about it later on. So the question now is, what happens if this resistor is changing? There's another resistor, or if it is a nonlinear resistor, or if there is a resistor plus a diode. Now I'm talking about cases in which these series elements are dissipated. That is, they are dissipating the energy passing through it and not storing it. And the case of storing will be like a inductor, which stores energy. I'll talk about it later on. So I'm now considering the case that this series element is dissipated. So the energy is lost, okay? Now, what is the difference between all these? There's actually no difference except for the speed or the rate at which the charge is accumulated, okay? If you put a larger resistor, the end result will be the same, but it just will take more time. Same thing for nonlinear, same thing for a diode. It will change the time, but it will not change the ratio of the accumulated energy and dissipated energy. It's the same thing. So we come to the conclusion that it really doesn't matter what is this element if it is dissipated. So this is very important. Now what about the discharging? Now if I discharge it by, say, this switch, then the input is 0. So I'm here, I'm starting here, and all this energy is of course lost, okay? And that doesn't matter if there is a large resistor or a small resistor, all the energy is lost to the dissipated element that I'm assuming, and therefore all the energy is really dissipated by whatever is here. Now you can say theoretically, what happens if you have no resistance? Well, there's nothing like this in the physical sense. I mean, there's no system without resistance. I mean, it could be very small. But let's talk about it theoretically. Suppose there is no resistance at all, okay? It's a superconductor that the resistance is 0. Well, what will happen is that you are going to have an infinite large current. And this infinitely large current will cause an electromagnetic wave that will remove this energy. This can be shown. I'm not going into it. This is something very theoretical. In reality, there is always a resistance, and this resistance is dissipating the power. And of course, it could be with a very high current, small resistance, or large resistance with a lower current, but the end result is the same. This is for discharging, and of course for charging is the same story. Okay, so let's look now at some different situations which we meet very often. And this is, I'm starting here with the case of a partial charging. That is, I have an input voltage, I'm charging the capacitor, but I'm not waiting to the end. I'm interrupting the charging here. So if you look at this picture, really the math doesn't matter. You understand what's going on here. Because for this part here, we already know that this energy stored in the capacitor is equal to this part here, like if this would have been the source. Now, as it turns out, our source is a higher voltage. So we are pulling this charge from a higher voltage, and therefore there is extra losses here. And this is the amount of these extra losses, okay? So therefore, I can write that the losses are, first of all, the original losses, like in the regular case of a charging to the end point, plus this area here, and you can write it in different way, and I'm not going to bother about it. Here it's only with Q and V, and here I've actually expressed it as a function of C, CV, VF squared over 2, plus this whole thing. So it's really simple to understand what is going on if you look at this chart, if you look at this relationship between Q and V, and then you can figure out just any situation that you might be interested in. So let's look at another case in which I'm tapping off. That is, the capacitor is charged and I'm recharging it to a given voltage, charged to Vs, and I'm charging it to Vin, and this is going to completion, okay? So this is like in the case of a bootstrap, for example, for a power supply for a high side gate driver will be the case that we are tapping off the energy from time to time, okay? Now if you look at it, you understand what's going on. The energy added to the capacitor is this thing, while the energy lost is only this thing here. And you can of course write it here, and it turns out that this energy lost is equal to this delta V squared over 2, which is a very well-known equation. This comes from looking at this triangle and figuring out the area of this triangle here, okay? So this is the area of this thing, and then it comes up to be this. Very simple. Next, we consider this situation in which, again, we are tapping off the capacitor, but we are not ending this process. For some reason, we are interrupting it here, okay? So the capacitor was charged to Vs with a charge of Q sub S. We feed in V in, starting to charge, and then we interrupt the charging here. This could be like if the time allowed is not sufficient, then we'll interrupt it at a given point, okay? So again, this is very, very simple. What you have to do is you have to figure out what is this area, okay? So I've done this calculation. I'm not going over it. It's very simple. You know, you just look at these deltas and figure out what is this thing. What I did, actually, I look at this triangle and then added this area here, and it comes to be like this expression. So let's do now here a sanity check. Let's assume that V in is actually Vf, okay? So this difference is 0. Then V in minus Vf is 0. Then this term is 0. And we get the expression we got before, delta V squared over 2. Now this brings about this idea of adiabatic charging. Adiabatic means without losses. And here is the idea. Now, if I have to charge a capacitor to this point, and if I do it in a separate way, by steps, charging it first to here, and then charging it from here to here, okay? And then charging it from here to here, these are the losses, as compared to the case that I'll charge it just by V sub 3, okay? And this will be the loss. Obviously, if this will be a more fine division of the voltages, then the losses are going down, and theoretically it could be 0. The catch here, making these voltages, is a lossy process. I mean, you have to have inverters or dividers or whatever, and then the end result may be that you are not gaining that much. But theoretically, if you could have provided a number of voltages and then use switches such that you'll charge the capacitor in this stepped way, then obviously you are gaining energy. Now what about the case of a resonant charging? This is really outside the scope of this presentation, but I thought that it'll be interesting just to look at this situation in the light of this Q as a function of V relationship. Okay? Now what happens here? It's a different story because we have an element which stores energy. So as we turn on the switch, current is starting to build up. Here it is, and I'm assuming that that the time is such that there is a resonant which ends. Okay, so there is a resonant behavior here, current going up and then going down. At this stage, I'm assuming that the resistance is zero. Okay, no resistance, so the current is going up. The voltage across the inductor is first in this polarity because we have V in. The voltage on the capacitor is zero, so we are charging this inductor with energy. The voltage of it goes down and down because the capacitor is, of course, gaining the charge and the voltage goes up until we reach this point at which the voltage here is zero. This is when V in equal to Vc, or Vc is equal to V in to be more precisely. At this point, the stored energy in the inductor is now being restored or harvested, you might say. There's no problem for the inductor to change polarity, and now the current goes this way, continuing. It is delivering energy to the capacitor from the inductor and also from V in. Okay? Both are adding this energy, and theoretically the voltage here will be twice the input voltage. Well, you can figure it out by writing differential equations, etc., but this is really what's happening in the physical sense. Now, if I look at this chart here, what I understand is that I have a process that goes up to here. This is the energy stored in the capacitor at this point. This now is not dissipated. It is stored, okay? Stored in the inductor. So now this energy, plus the energy from the source, is continuing here the charging up to this point. So this is theoretically a lossless process. However, there is no inductor and there is no circuit without resistance. Can't have it. Now the effect of the resistance here is that along this way you lose energy dissipated by this resistor. Secondly, the peak current will be different and the voltage will be different because you are losing energy. Okay, I'm not doing it here because this is, as I've said, a little bit outside of the scope of this presentation. Now, the energy lost is, of course, the resistance times the RMS during this period. So you have to figure out what is RMS. This is not, if this is a resistance, this is not sinusoidal. There is a correction factor depending on the quality factor of the circuit, okay? So you have to figure out what is the RMS of this thing, and then this will be the energy loss. So this is the case of resonant charging. Let me move now to a nonlinear capacitor. So a nonlinear capacitor is a capacitor in which this is not a straight line, this relationship between Q and V. Therefore, there is no one capacitance you can speak of. You can define, first of all, in general, two classes of capacitances. One is the total capacitance, that is, if you are at this point, then the ratio between the Q and V is this total capacitance. But then you can define the local or derivative capacitance, which is the derivative or the slope here at any given point. Both of these depend on the operating point, so there's no one value. It is changing all the time depending on where you are at. Of course, if it's a small signal, you're working at one point here, then you can talk about a certain C sub t and a certain C sub d, but this will be for small signal. Once the signal is large, or if you're moving to another point, this is incorrect. So it's very important to realize that. Nonetheless, this generic representation holds in this case too. So in this case, this is the energy stored in the capacitor, and this is the energy lost. As you can see that for this particular curvature, the energy stored in the capacitor is smaller than energy lost. That is, the loss is larger, so it's not half, okay? Half of the total energy. It's not divided by a straight line here into two halves. So this relationship now between energy stored and lost depends on this curvature and your operating point. Let me now illustrate the usefulness of this representation by considering the case in which I have a linear capacitor charged to a given value, and then a nonlinear capacitor charged to another value of voltage, and I am now connecting these and charging, say, the nonlinear capacitor by the linear capacitor. Now the conservative parameter here is the charge. During this process of charging and discharging, charge is not lost, energy is lost, but charge remains. Okay, it's moving from one capacitor or from a source to a capacitor, one capacitor to another, but charge does not dissipate, does not run away, unless, of course, you are passing it through a resistor to ground or across a capacitor, then you are sort of removing the charges. But when you have two capacitors connected, then the total charge remains. It's moving from one capacitor to another. So what we can do is a method that has been used many years ago in connection with amplifiers and loads, and that is to look at the problem in a graphical way. So what I'm doing here is that I have this relationship here, this plot here of the nonlinear capacitor, and then on top of it, added to it, sort of, I have this one now reversed, okay, it's top down, such that the total charge, that is this charge plus this charge, are as they were before. So I'm maintaining this requirement that the total charge is always the same. Now what happens here is the following. We started with energy in here, this is this energy, and this is this triangle here. This one has this energy in the capacitor, and this is this triangle here. So this is the energy that we ended with after we connected the two capacitors, and obviously this is the energy lost. So you can see that you can do it very nicely. Obviously you can write equations that will describe this situation, but this gives you an understanding what is really going on when you connect this linear and nonlinear capacitor. So this brings me to the end of this presentation. I hope you found it of interest. I like very much this representation of Q as a function of V, and perhaps it will be useful to you in the future. Thank you very much.